Today our topic is Radix to DIT FFT algorithm. We first study about basic idea of Radix to algorithm. While calculating DFT, we have discussed that we always calculate endpoint DFT. The number n can be factored as n is equal to R1, R2, R3 Rv. Here every R is prime. Now if R1 is equal to R2 is equal to R3 and Rv is equal to R, then we can write n is equal to R to the power v, and this equation termed as equation number 1. Here R is called radix or base of the FFT algorithm and v indicates the number of stages in FFT algorithm. Now if R is equal to 2, then it is called as radix to FFT algorithm. Then equation 1 can be written as n is equal to 2 to the power v. This equation termed as equation number 2. Thus, if we are computing 8-point DFT, then n is equal to 8. So, from equation number 2, it can be written as 8 is equal to 2 to the power v and v is equal to 3. Therefore, for 8-point DFT, there are 3 stages of FFT algorithm. Now, we have listed some property of Twiddle factor used in FFT. First one, Wn to the power k plus n is equal to Wn to the power k. Second one, Wn to the power k plus n by 2 is equal to minus Wn to the power k. And third and final one, Wn to the power 2k is equal to Wn by 2 to the power k. Now we are go to Radix to decimation in time or DIT FFT algorithm. What decimation means to break into parts. Here DIT indicates dividing or splitting the sequence in time domain. If we use DIF, then dividing or splitting the sequence in frequency domain. Let xn be the given input sequence with length n. Now for decimation in time, we shall split xn into 2 parts. Even index samples gm, and gm is equal to x of 2m and m is equal to 0, 1 n by 2 minus 1. And odd index samples hm is equal to x to the power 2m plus 1 and m is equal to 0, 1, n by 2 minus 1. So that we can write xn is equal to gm plus hm, and this equation termed as equation number 3. Now according to definition of DFT, we have xk is equal to summation of n is equal to 0 to n minus 1 xn wn to the power kn, where k is equal to 0, 1, n minus 1 and wn is equal to e to the power minus j 2 pi by n. Now according to equation number 3, xk can be written as summation of even numbers of n to n minus 1 xn wn to the power kn plus odd numbers of n to n minus 1 xn wn to the power kn. Now we replace odd number of n as 2m plus 1 and even number of m replaced by 2m, so that equation become xk is equal to m is equal to 0 to n by 2 minus 1 x of 2m wn to the power k into 2m plus m is equal to 0 to n by 2 minus 1 x of 2m plus 1 wn k 2m plus 1. Now x of 2m replaced by gm and x of 2m plus 1 replaced by hm. Now here 2m plus k split as wn to the power k 2m into wn to the power k. As because wn to the power k not depend on m, we can extract outside from the summation wnk and xk written as m is equal to 0 to n by 2 minus 1 summation of gm wn to the power k 2m plus wnk summation of m is equal to 0 to n by 2 minus 1 hm wn k 2m. Now putting the third property of Twiddle factor, here wn k 2m written as wn by 2 km, same as here also, so that wk is equal to m is equal to 0 to n by 2 minus 1 gm wn by 2 km plus wnk m is equal to 0 to n by 2 minus 1 summation of hm wn by 2 km. Now if we consider gk and hk is n by 2 point DFT of gm and hm respectively, so that gk is equal to m is equal to 0 to n by 2 minus 1 gm wn by 2 km. It's basically n by 2 DFT of gm, and same as gk, hk also written as a summation of m is equal to 0 to n by 2 minus 1 hm wn by 2 km, and xk is equal to gk plus wnk hk. The n by 2 point DFTs of gk and hk are periodic with n by 2 periods, so that we can write g k plus n by 2 is equal to gk according to property of DFT, and also h k plus n by 2 is equal to hk. But wn to the power k n by 2 is equal to minus of wnk according to second property of Twiddle factor. Hence, if xk is equal to gk plus wnk hk, then xk plus n by 2 is equal to gk minus wn to the power k hk. Now we study about butterfly diagram. First we take gk and hk, and gk and hk added as gk directly and hk multiplied by wkn, and result is xk, and also for xk plus n by 2, this is gk plus minus of wkn into hk. This diagram basically shows like a butterfly. That's why we called this diagram as butterfly diagram. Now, first stage of decimation of 8-point FFT. We take some data of xn, say 8-point data, x0, x1, x2, x3, x4, x5, x6, x7. First, we split it into odd and index samples. Like HM is for even samples, x0, x2, x4, x6, and GM is for odd samples, x1, x3, x5, x7. Now we compute 4-point DFT of HM and we got H0, H1, H2, H3 whole as HK, and another 4-point DFT for odd samples and we got G0, G1, G2, G3 and this sequence named as GK. After that, we just add as butterfly diagram with some H0 some HK samples and some from GK samples, like X0 taken as H0 plus G0 into W n to the power 0. Again H1 added with G1 into W1 n and result as X1. Same as X2 and X3. But for next 4 samples, G0 multiplied with negative twiddle factor, like H0 added with minus W4 n into G0 and resultant is X4, same as X5. X6 also added with H2 plus G2 into minus of W6n and X7 calculated according to H3 plus G3 into minus of W7n. This is the first stage of decimation 8-point FFT. This same idea can be applied for calculating 8 by 2 or n by 2 DFT of the sequence GM and HM. In above case, this is 4-point. It can be obtained by splitting again GM and HM into their odd and even index samples. This idea can be applied for recursively log base 2 of n times of n is power of 2. If n is equal to 2 to the power v, then final stage sequences are all of length 2. For a 2-point sequence, xn is equal to x0, x1, the DFT is like xk, n is equal to 0 to 1 summation of xn w2 to the power kn, where k is equal to 0 and 1. So that capital X0 is equal to x0 w2 to the power 0 plus x1 w2 to the power 0. Here w2 to the power 0 can be neglected as w2 to the power 0 is equal to 1. So that x0 is equal to time domain x0 plus x1. Now for capital X1 is equal to x0 into w2 to the power 0 plus x1 w2 to the power 1. w2 to the power 0 is equal to 1, but w2 to the power 1 is equal to minus 1. So that capital X1 is equal to x0 minus x1. If we diagram the 2-point DFT, then we get a diagram like this. From this, we can notice that we can easily calculate 2-point DFT as the frequency domain sequences are as first one summation of 2 time domain sequence, second one the subtraction of 2 time domain sequence. For 8-point DFT, we split the xn into even and odd parts named as GM and HM. Now for 4-point DFT, we split GM and HM into their even and odd parts. P1 and P2 contains even and odd parts of GM respectively. So that we can write GM is equal to P1L plus P2L. And Q1 and Q2 contains even and odd parts of HM respectively. So that HM is equal to Q1 plus Q2. So Xn split into GM and HM, and GM split into P1 and P2, HM split into Q1 and Q2. Next, we draw the pictorial view of splitting the index of Xn. First, Xn is like x0, x1, x2, x3, x4, x5, x6 and x7. We first take even sequence of Xn named as GM. They are x0, x2, x4, x6. And odd samples are called HM, and they are x1, x3, x5 and x7. Again, GM split into even and odd part, and even part named as P1L, and this one will be G0 and G2, and G0 is equal to x0 and G2 is equal to x4. This one G0 and this one G2. And odd part named as P2L, G1 and G3. This one G1 and this one G3, so that x2 and x6. HM also divide into even and odd part. Even part named as Q1L, and this contains H0 and H2. H0 basically x1 and H2 basically x5. And odd sequence samples are called Q2L, H1 and H3. H1 basically x3 and H3 basically x7. This is the pictorial view of splitting the index value of Xn. It showed that the n is equal to 8 initially input sequence like that, x0, x1, x2, so on. The first split requires the data to be arranged as follows: x0, x2, x4, x6 and x1, x3, x5, x7. In the second and final split, The data appears in following order: x0, x4, x2, x6, x1, x5, x3, x7. Here, index can be calculated by using a very easy method called bit reversal method, like as following. If we take 3 bit like x, y and z, if you use bit reversal method, then final formation will be z, y, x. Say original indexes are 0, 1, 2, 3, 4, 5, 6, 7. If we convert this into binary domain, then we get 0, 0, 0, 1, so on. Now, we applied bit reversal method. Here, 0, 0 going to be 0, 0, 0, 0, 0, 0, 0, 1 going to be 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1 change into 1, 1, 0 and so on. So that final indexes are like 0, 4, 2, 6, 1, 5, 3, 7. So in this way we can easily calculate the final index value. Now this is final representation of 8-point FFT. We take 8-point sequence of xn, x0, x1, x2, x3, x4, x5, x6 and x7. According to bit reversal method, first we take x0, then x4, then x2, x6, x1, x5, x3 and x7. Here n is equal to 8, so that there are 3 stages, because n is equal to 8 means 8 is equal to 2 to the power 3, and so that number of stage will be 3. Here first we compute 2-point DFT between x0 and x4. Same for x2 and x6, x1, x5 and x3, x7. So here we compute 4 2-point DFT and we get 8 output. So second stage, first 2 output taken as same, and third and fourth output multiplied with w0 to the wn to the power 0 and wn to the power 2 respectively. And after multiplication we take output multiplied with -1 also. Now here we use butterfly addition. First 2 added with second 2 with -1 multiplication, and second 2 added with first 2 remains same. Same thing happened for bottom 4 output. In third stage, first 4 output taken as same, but next 4 output multiplied with wn to the power 0, wn to the power 1, wn to the power 2, wn to the power 3, and as well as multiplied with -1 before addition. Here also we use butterfly addition. First 4 output of second stage added with bottom 4 output multiplied by -1, and bottom 4 output added with top 4 output remains same, and we got the x0, x1, x2, x3, x4, x5, x6 and x7. So here 3 stages are colored with, first stage colored with blue, here we compute 2-point DFT. Second stage colored with orange, here we use butterfly addition, and for added with top 2 and bottom 2. And in third stage colored with green, here we use butterfly addition for top 4 and bottom 4. And this is the final representation of 8-point FFT. Thank you.